All right, let's pick it up where we left off. There are two more items here after our kind of the main piece of this section, just how to do implicit differentiation on implicit equations like those. What else do we have here? Second derivatives. How do we take higher order derivatives with implicit differentiation? Now, usually when I announce this, students like gasp, like, oh, this sounds insane, doing higher order derivatives. It might not be as bad as you think. And really the emphasis in this section and in your homework are on first derivatives. We do want to recognize second derivatives exist. How do we perform them? Let's look back at our first example, x squared plus y squared equals 25. So we found the first derivative. I'll skip all of the steps to get to here. We found it as dy over dx equals negative x over y in the end. So how would you take a second derivative? Okay, well, working from that first derivative, we can just go right on ahead and we'll use whatever means we need. We can see, hey, if the first derivative is this quotient, negative x over y, let's perform a quotient rule, taking note when we're taking the derivative of x, when we're taking the derivative of y. And so here's what that quotient rule would look like, right? Low d high is -1 minus the high times the d low. The low is y, so the d low is dy over dx. Low d high minus high d low, and it's all over the low squared. Okay, well, this is fine, but notice, right, there's some obvious things that we can simplify. Let's actually go ahead and do that. Just clean up some of those negatives in the numerator. So this seems fine, but notice that now we're calling the second derivative, we've got it in terms of x and y, but also in terms of the first derivative. We really want to avoid that. We'd really like to have the second derivative just in terms of x's and y's. Well, is that possible to do, or are we just stuck with this? Does it have to be in terms of the first derivative? Well, if you look closely, hey, yeah, a dy over dx appears here, but we know that dy over dx is equal, in this case, is equal to negative x over y. So we can substitute negative x over y in for that first derivative, like so, just simply replacing it. And then we can continue simplifying, and eventually we'll have the second derivative in terms of just x's and y's. So let's see, if we multiply there, right? Our numerator is negative y minus x squared over y, and that's all over y squared. Now, hey, we've got our second derivative just in terms of x and y, not in terms of the first derivative at all. But we want to continue simplifying. Ooh, this is good practice. How would we simplify that further? So notice we've got this fraction inside of a larger fraction. Its denominator is y. So why don't we multiply the top and the bottom here by y? That won't change the value of the expression, but it will let us cancel out here. So this numerator, if we multiply by y, this y will distribute to both terms, canceling here, and then we can multiply the denominator by y, and there's our simplified second derivative, negative y squared minus x squared all over y cubed. Kind of interesting how that plays out, right? The original was x squared plus y squared, and the second derivative had a negative x squared, negative y squared. I don't know, probably total coincidence, but that's kind of interesting. So if you need to take a second derivative, again, just kind of do whatever you need to do based on the first derivative. And then when those dy over dx's appear, we know we can always substitute to get it all in terms of x's and y's. You could keep going, right? We could take a third derivative if we wanted, right? Dy over dx would appear again. That first derivative is always going to come back, but we can always go ahead and replace it and clean it up. Okay, so that's one of the topics here towards the end of the section. What's the last topic? We're going to look at the derivatives of the inverse trig functions. And I know this like comes out of nowhere, like, what? I thought we were done with the trig derivatives. Well, we recognize, yes, we know the derivatives of the 6 trig functions, but there were also 6 inverse trig functions. We didn't have the foundation to figure out what those were back in 3.3. So we're going to do that now with implicit differentiation. What is the derivative of inverse sine of x, or you might call it arc sine of x? So this is pretty clever how this comes about. We're obviously going to use implicit differentiation. We're going to start by saying, hey, let's call our function y. Let's call it y equals inverse sine of x. And we're going to try and figure out what dy over dx is. Well, we can't do it directly, but what we can do is kind of play with this and then use implicit. So we can take the sine of both sides. So if we take the sine of the left, it's obviously just sine y. If we take the sine of the right, the sine of the inverse sine and inverse sine obviously are inverses, they cancel out. And that would leave us with just x. So these statements mean the same thing, sine of y equals x. Okay. Now notice we can take the derivative of both sides. We're able to find the derivative of sine y. If we apply a d over dx to both, and then use implicit differentiation on the left, it would give us the cosine of y times dy over dx. And that would equal the derivative of x, which is just 1. And look at this. If we then solve for dy over dx, we get 1 over the cosine of y. Now that's pretty nifty. And I guess you could argue that we found it. We found the derivative of arc sine x, and it's 1 over cosine y. The thing is, that's pretty good, but kind of like that previous discussion in the second derivative, we really just want this derivative in terms of x. We've got it in terms of y, and that's okay. Thing is, the arc sine of x, we do think of this like a function. And so we want our derivative to be a function of x and just be in terms of x. So how we normally think of derivatives of functions. Okay. What are we going to do? How are we going to get this in terms of x? I mean, cosine of y, what do you do with that? We're going to go back to our Pythagorean identity. Cosine squared y plus sine squared y equals 1. And we're going to do a little bit of work with that. So just using our Pythagorean identity, what if we were to solve for the cosine of y? If we isolate cosine y, right, if we subtract sine squared y and then take a square root, it would give us the square root of 1 minus sine squared y. Like, okay, like, so what? How is that helpful at all? This is getting more complicated. But look, sine squared y is in that, right? And up here, sine of y equals x. So this sine y we can replace with x, and we can say that the cosine of y is equal to the square root of 1 minus x squared. So what we're going to do is replace this cosine y here with our 1 minus x squared, and there we got it. Dy over dx, the derivative of arc sine x is 1 over the square root of 1 minus x squared. Thank you to that Pythagorean identity. Okay. I'm just going to tell you the rest of them. Here it is to wrap up our section, the 6 inverse trig derivatives. We've got the derivative of arc sine of x, what we just saw, 1 over the square root of 1 minus x squared. The derivative of arc cosine of x, look at that. It's the same, just negative, -1 over square root 1 minus x squared. Interesting. The derivative of arc tangent x or inverse tangent x, that one doesn't have a square root. That's pretty sweet. 1 over 1 plus x squared. Inverse cosecant x, -1 over x square root x squared minus 1. Inverse secant x, +1 over x square root x squared minus 1. And inverse cotangent x, -1 over 1 plus x squared. Now, this probably seems kind of overwhelming, like, wow, I just dumped 6 derivative rules on you basically at the end of this section. Yeah, and you got to know them. We're not going to do any examples here in the lecture. I mean, you can take these and figure out homework problems with this. I think we have enough practice taking derivatives that we could use these within product rules and chain rules and other sorts of things. But just kind of notice some of the patterns. So we again have these friendships. Sine and cosine are identical. It's just that cosine is negative. Same thing with the inverse tangent and cotangent. Now they are not friends. They're friends, inverse friends, I guess. The inverse cotangent is the same as tangent but negative. And then inverse cosecant and inverse secant are identical. Just that the secant is the positive cos. So again, we have the same, that all the cos are negative, right? So there's really just 3, that you have to know, maybe like inverse sine, inverse secant, inverse tangent, and then the cos are the negatives of those. And probably the secant, inverse secant is the hardest one because it switches the order in the square root, and then there's an extra x there, but it is what it is. All right, you guys, that is the end of 3.5. So let's stop this one here.